Q and R factors in reverse order, and I overwrite A with that. And then I just repeat the process. So, all right. So now I can re-describe orthogonal iteration this way. Better time than I thought. It helps to skip the parts you don't really like anyway. So this algorithm is called QR iteration. Oh boy. All right, so you don't have to choose Q not equal identity. That's a convenient choice. But you do need to choose it, so that's a unitary matrix, so you could choose identity. And you define T0 to be Q0 Hermitian transpose A Q0. So in the simplest case, you just make that A. All right. So then what you can do is I can take TK minus 1 and QR factorize it. So this matrix is unitary. So UK Hermitian transpose UK is equal to identity, and RK is upper triangular. Okay. And then I form my next matrix from my sequence just by multiplying these in the opposite order. Right. Now, that's it. You keep doing this until convergence if you actually get convergence. Now, what I would encourage you to do is actually try this out in MATLAB. So for instance, go ahead and make a random matrix of a certain size. I'll just say like a 6 by 6 matrix. And then you do the following repeatedly. You use the QR command, whoops, to compute the QR factorization. And then you overwrite A with those factors multiplied in reverse order. So you just repeat these two steps. Here's what you will observe. The matrix will eventually, it'll take quite a while, assume a quasi-upper triangular form. It won't be completely upper triangular, generally. The reason why you won't get that is a randomly generated matrix, chances are going to have at least two complex eigenvalues, and those are equal in magnitude. So eigenvalues that are equal in magnitude will prevent this from converging entirely to upper triangular form, but at least you'll get like a quasi-upper triangular form where it's like block upper triangular, where you have 1 by 1 or 2 by 2 blocks, depending on whether you have distinct real or complex eigenvalues. So you will observe this effect of converging to something useful that's actually eigenvalue revealing. The problem is you will find that it takes a lot of iterations, even with a small matrix, to get there. So there are two huge glaring drawbacks to this process, even though it's something that actually is the first effective algorithm that I've shown you for computing all the eigenvalues of a matrix. But one big problem is the convergence is very slow. What you would notice is if there's eigenvalues that are spread out from the rest, that are isolated, it'll converge to those very quickly. But if you have eigenvalues that are complex or clustered closely together, it'll take a lot more time to make that part of the matrix upper triangular. So that's one drawback. The second drawback is each iteration we're computing a QR factorization. How expensive is a QR factorization? Order n to what?
It's square.
What?
It's square. Cube.
I wish.
It's cubed. I don't know.
Yeah.
Cube.
Yeah.
It's my second
Square
guess.
wouldn't be so bad.
This was second
But
guess.
it's order n cubed. Think about Gaussian elimination, the whole thing, order n cubed. Cholesky, order n cubed, the whole process. But imagine doing order n cubed work per iteration, and you're also doing at least order n iterations, if not more. Maybe order n to the fourth algorithm. That's totally unacceptable. So we have some work to do. And that's what I'm going to show you starting next week, is how we can actually address both of these issues. We can actually make each iteration order n squared in unsymmetric case, and order n in the symmetric case. And also how to speed up convergence, how we can modify this iteration just a little bit to find each individual eigenvalue more rapidly than this will. But at least now we're really getting somewhere in terms of being able to find eigenvalues. Okay, 5 minutes. I can make one useful point here. There is a variation of the power method that people find quite useful. Suppose you don't want all the eigenvalues and eigenvectors. Maybe you just want selected ones. Now, if you want the largest one, you just use the power method, and it's all you care about. But if you want different selected eigenvectors, you can use what is called inverse iteration. Inverse iteration is nothing more than the power method applied to A minus mu times identity inverse. So instead of multiplying by A, you're multiplying by A minus mu I inverse. No, you're not computing the inverse. That rule is still in force. But you'd be solving systems involving A minus mu I. And the value mu is called a shift. That's a scalar of your choosing. So the algorithm is you choose Q naught, and then you iterate as before, and you solve A minus mu identity zk is equal to qk. So now you're solving a system for zk. Zk is your unknown. And then you normalize like you do in the power method. So you just divide by its 2 norm. And that's it. Now, keeping in mind that the eigenvalues of the inverse are the reciprocals of the eigenvalues of A. And also, if you shift your matrix by mu times identity, that subtracts mu from all the eigenvalues. So, inverse iteration finds the eigenvalue. Which eigenvalue is it going to find? Oh, look this way. It's going to find the largest eigenvalue of A minus mu identity inverse. But in terms of the eigenvalues of A, what's it going to find instead of the largest?
I know, that's probably like smallest, because
Well,
that's the only
okay,
one.
okay, yeah, well, yeah, it's going to find the smallest eigenvalue of A minus mu identity, but because you're shifting by mu, what eigenvalue of A will it pick up?
The
Lambda
mu.
minus 1.
Mu. That's what I was
What?
gonna say.
What?
What are you saying?
The. Never mind. Never mind.
Assuming that mu itself is not necessarily an eigenvalue of A.
Right.
We don't want to
But
be.
it's just, okay.
Okay. So yeah, so it's finding the smallest eigenvalue of A minus mu identity, but the eigenvalue of A corresponding to that, man, that ring looks awful.
Yeah.
And
You have no umbrella?
I like my
Oh,
umbrella.
someone's picking me up. You can use mine. Just waiting for the.
In the interest of time, it finds the eigenvalue closest to mu.
Yeah.
Okay.
Oh,
Closest to mu.
Yeah.
Because of my phone.
Okay. Because that is going to be the smallest
Nope.
eigenvalue of A
I
minus
have
mu
the answer
identity,
right
an
in front
absolute
of me.
value. Okay. So it's a good idea to use this if, like for instance, suppose you find all these many eigenvalues. You can use your approximate eigenvalues as shifts, and then you can only perform. You go ahead and perform inverse iteration, and maybe carry out just one iteration, and bam, you have the eigenvector. So, so this is a good idea if you only need like maybe less than 25% of the eigenvectors. This is a good guideline. Okay, and the last point I'll make is another variation of inverse iteration is called Rayleigh quotient iteration. And what that is you use A minus mu k identity inverse, where mu k is equal to qk Hermitian transpose A qk. This is called a Rayleigh quotient. Actually, to give you a proper definition of Rayleigh quotient, what I should do is divide this by qkh qk, but that equals 1, so I don't really need to include that in this case. However, this is only useful if A is symmetric. So this is useful for finding selected eigenvalues and eigenvectors of a symmetric matrix. And the really nice thing about this algorithm, it's rather unusual, it converges cubically. In other words, the number of correct decimal places in your computed eigenvalue is roughly going to triple from one iteration to the next. It is lightning fast. But in terms of number of iterations, but each iteration might be kind of expensive. So these are two useful variations of the power method in practice. But what we'll focus on next week is how to carry out, how to improve a QR iteration to find all the eigenvalues of a matrix instead of just selected eigenvalues and eigenvectors. Okay. And I'm over time. Oh, the rain calmed down a little bit.